All right, folks, it's time for our favorite podcast, Cut to the Chase. I am here with Dr. Adam Leibovich, my favorite physicist. He has actually appeared on the show numerous times. He gave us a whole series on the universe, 101, numerous episodes. And then we follow that up by talking about actually some new stuff going on in the world of physics, astrophysics, all that kind of stuff. We talked about the standard theory and the muon experiment. We talked about James Webb Telescope, what we were hoping it would discover or see for us. And we also talked about nuclear fusion and the advancements in nuclear fusion. Is it really still 30 years away? Could that be something that helps us transition off fossil fuels? So how are you doing today, Dr. Leibovich?
I'm doing great, Greg. How you doing?
I'm doing wonderful. Thanks for coming on. And the biggest update of all, of course, is a major congratulations. Dr. Adam Leibovich is now the Dean of Arts and Science at University of Pittsburgh. So I don't want to forget about that. And major congratulations about that, Adam.
Thank you. Thank you very much.
All right. So I think we're going to start today talking about the standard model. And because we got new updates on all these things, the standard model and the muon experiment. So I want to just pretend like I know what I'm talking about. The standard theory, the standard model basically explained all the components of the universe, and it didn't cover everything. It didn't cover gravity.
Right.
It didn't cover dark energy.
Right.
All right. And yet there were numerous experiments done with the standard theory to basically determine whether it was as accurate of a theory as could be. Yet that really, despite all those experiments turning out to be proving what was hoped to be proven, the continuation of the experiment is ongoing. Would that be accurate to say?
Yes. So the standard model works extremely well. It does not cover gravity. So we know that there is work to do to combine the theory of gravity, which is Einstein's theory of general relativity, with what's called the standard model of particle physics, which covers the other four fundamental interactions that we know of at this time. So there are four fundamental interactions. Gravity is one. There are three others. The standard model covers those three. Gravity is the fourth. We do not have a complete theory, as you pointed out. The standard model does not explain dark energy or dark matter. And there are other holes in our knowledge if we just look completely at the standard model and on gravity. And of course, combining them together is a big challenge.
All right. So we did one earlier episode on this muon experimentation, maybe about a year ago, and the wobble. I remember there was, something about the wobble that essentially revealed the fact that there might be new physics.
Right. So the muon and the electron, and really pretty much any charged fundamental particle, has what's called a magnetic moment. So basically, these particles act like tiny little magnets. So the magnetic moment of the muon and the electron is something that we know of. We can measure the size of it. If we estimate the size, sort of the quickest, sturdiest estimate, it depends on the charge of the particle, the mass of the particle, and what's called the spin of the particle. And those three things are extremely well known from our measurements, really from measurements. So we know those things extremely well. So combining those together, we get a prediction for what the magnetic moment of these particles are going to be. So if we focus on not the mass part, the electric part, and the spin part, there's a coefficient in front, which happens to be 2. Why it's 2 is because when you add relativity to the picture, which we know exists, it turns it from a 1 to a 2. It was sort of a surprise a long time ago. That's well understood. Now, it turns out that quantum mechanical effects change it from the 2 by a tiny little bit. And so there's been, for 60 years or so, people have been calculating, longer than that actually at this point, have been calculating these small corrections to the magnetic moments of the electron or the muon. So we measure this in something called G minus 2, where G is the thing which is close to 2. So we subtract off that 2, which we kind of know about. And then there's small corrections to that. For the electron, we know it to 10 significant figures. So we know it unbelievably well. For the muon, we know it not quite as well, but we know it fairly close to that amount. And we know it in 2 different ways. We know it by the calculation, the theory, and we know it by an experimental measure. And by comparing those 2, we can see whether our theory is working, holding up to reality, to the experimental result. And what you were pointing out is that there is a new measurement which measures this quantity, G minus 2, for the muon more accurately than it had been measured before. And there is potentially, and this is where it gets complicated, potentially a difference between the experiment and the theory.
Okay, and what would that be, and what's the significance of this?
Okay, so if there is a discrepancy, we need to make sure our measurement's correct, and we need to make sure our theory is correct. But if that holds up, if that difference holds up, that means we're missing some physics. So there's something fundamental that would need to be added to get that correction. Now, it could be that we missed something when we did the theory calculation. It could be that we didn't quite get the measurement exactly right. So we still need to make sure that those 2 things are true. But eventually, if this difference remains, then that will mean that there's something fundamental that we are missing. Now, the interesting thing is when you're doing the theory calculation, there's lots of different pieces which you need to add up. And one piece is particularly hard. And we have 2 ways to get that piece. And it turns out that these 2 methods give different results. And we don't know which one is correct. But one of them, which until recently was the less trusted way of getting that piece, actually gives the theory consistent with the experiment, while the more traditional way of getting that piece gives this discrepancy. So this is a new thing that we need to try to figure out, why these 2 ways of extracting this one part, which is a tiny little bit, but it's important, whether it's one part, which one is correct, because it could be that the standard model is working extremely well, as it has, for 60 years, or it could be that the older, more traditional method is correct, in which case we have a real discrepancy between theory and experiment, and then we will be trying to figure out how to
explain it.
Physics. Yeah, explain it.
So that would be new things or new particles that we never realized are in the universe.
That would be the way in a particle physics frame of mind that we would explain it. There would have to be something new, which is entering into these complicated calculations, which when we say something new, that's basically a new particle interacting with the muon and the electrons and the other fundamental particles, which slightly changes the muon magnetic moment, this G minus 2 value.
All right, so who is doing these experiments? Is this like everybody out there doing it, or is it one group?
So there's a couple different groups who have been working on this at different times in history. Right now, the most recent result came out of Fermilab. And then there are a number of groups working on the theory part.
All right, and so when, I guess the quark was one of the latest things that was discovered as part of this whole what's in the universe.
Well, the quarks we've known for quite a while. That was something that we've known since back in the 70s, late 60s, depending on how firm you wanted to say we actually knew about them. I mean, there was evidence of them from the 60s. Sort of our understanding of the quarks were really firmed up, you could say, in the 70s. The last quark to be discovered was the top quark, which was predicted long ago, but was discovered back in the early 2000s. It was finally observed. Since then, the only other fundamental particle that was missing was the Higgs boson, which was discovered back in 2012, if I remember correctly, is when it was announced.
All right. So just to like simplify the Standard Model and the universe, you're basically talking about the objective to some degree sounds to be, hey, let's figure out what the entirety is that's out there in the universe.
Right. The entirety of, so what's the building blocks? So what are the particles that make up everything in the universe and the interactions between those particles? So that's really what particle physics is aiming to do, is truly trying to find, essentially, you could say, the fundamental equation which governs the universe.
All right. And so, you know, I keep hearing when I read up about Standard Model that they've run these experiments to basically determine what is the objective? Right. I mean, is that to see, are we missing something, or what are we missing, or both?
Right. So we are continually probing to search for things which don't agree with the Standard Model. And you can either run very high precision experiments like this muon G-2 measurement. So if you are measuring it extremely precisely, you might find one of these discrepancies. So that's one type of experiment that people are doing. Another type of experiment is more exploratory. You're just smashing things together, see what comes out, and seeing if there's anything which disagrees, any new particles or other discrepancies, which might not be as deeply hidden as the G-2 discrepancy.
What would be like the simplest experiment that has been run, you know, to figure out the standard theory, something that anybody can basically
to see if there's something new?
Yeah, I mean, over the course of time. Dropping an apple from a tree.
This has happened. So you smash things together.
Yeah.
And some new particle comes out that was totally unexpected, that we don't have an explanation for given the current knowledge. So back in the say 70s, you smash things together, and we didn't really understand everything. The Standard Model wasn't really complete at that point, but there was what was called the November Revolution, because back in 74, they smashed things together and a new type of particle came out totally unexpected. And that opened the floodgates for a whole bunch of new things coming out that was not really able to be explained with the physics that we had previous to that. It took a little while to sort it out and make sure we understood everything, but that sort of was building up the Standard Model to where we are today.
All right. So when you conceptualize about the entirety of the universe, and okay, our objective is to figure out what it consists of entirely, how far along the process do you think we are? I mean, is this something that's never going to end, or are we going to actually, you could see the field of science saying, we got it?
I think that we are nowhere close to really being at the end of science. So I think that it's not really possible to say how far along that path we are.
Yeah.
There's going to be new things to discover for well past all of our lifetimes. So, there was a time back in the late 1800s where people thought that they knew everything.
Yeah.
And there were a couple things that didn't really quite make sense, but they figured out, we'll figure it out. It's just a little, little bit of details. And then suddenly we discovered relativity, for special relativity, general relativity, quantum mechanics, and we discovered new things out in space that we had no idea of what they were. We discovered the expansion of the universe. All these things were not even imagined back at the time. And people were saying, oh, we're basically done. So I don't want to say that we're anywhere close to being done.
All right, so let's shift topics now to nuclear fusion, which is one of my favorite topics. And there's been some advancements in that field. And we did have a discussion about this when the first breakthrough, or one of the last breakthroughs occurred, which was, from my understanding, that the amount of energy that was needed to create the fusion was less than what the energy that came out. But that did not take into account the engineering part of the process, which, if you factor that in, it was not a net creation of energy. And now it looks like they did an advancement, which is critical in that it created even more energy. And also what was critical about it was that they were actually able to replicate that experiment.
Yes, that's exactly right.
All right. So let's explain I know we've already done an episode on this, but let's explain how nuclear fission, which is what's in use now when we talk about that, differs from nuclear fusion. And if you could even throw in, the atomic bomb and where that fits in with this whole equation.
Given the Oppenheimer movie right now,
it's
quite relevant. So there's two types of ways you can gain energy from atoms. There's fusion and there's fission. So fission is when you take a particle and you break it into smaller particles. Okay. This happens naturally for some heavy particles like uranium, like plutonium. There are other examples out there as well. So it happens naturally. What happened when we built an atomic bomb, so like in the movie Oppenheimer, or if you are talking about what happens in nuclear reactors that we have now, you have to, first of all, purify the uranium, because if you get a certain type of purified uranium or plutonium, what can happen is a chain reaction where when the uranium, say, nucleus falls apart, it will spit out a whole bunch of particles, including other neutrons, which then can hit other uranium nuclei, which causes them to split. And by this happening, you can have one go, which then breaks up 2 or 4, and then it just has an exponential increase, and it releases a huge amount of energy. That's what happens in a bomb. Okay. In a nuclear reactor, you don't want a huge explosion. No. That would be bad.
That would be bad.
So what they do is they put in essentially objects, which rods that are barriers, which stops or can control the amount of this chain reaction, so it doesn't grow out of control, and they can make it so that they're controlled rates. Okay, so by breaking apart these large atoms, you release energy. Another way you can gain energy is by taking very, very light atoms and combining them together into heavier ones. Okay, so this is what happens in the sun or stars in general. You take light particles, beginning with most in stars is hydrogen, and you take the hydrogen and you fuse them together to make helium. It also releases a lot of energy. So that's nuclear fusion. So you're fusing things together. Okay. That's the goal of these new type of experiments. And there's different ways you can create fusion. The hydrogen bomb created fusion by having some hydrogen, which then atomic bomb went off, pushed the hydrogens together to cause it to fuse, and that caused an even bigger explosion. So that's why a hydrogen bomb is more powerful than an atomic bomb. So a hydrogen bomb has both fusion and fission happening in it.
Okay.
We don't want to have a big explosion in our power plants. That's a bad thing. So we're trying to come up with other ways to cause fusion to happen. You could do it in the center of a star. That's kind of hard to replicate on the Earth, but we're trying to essentially replicate that in a controlled way. There's two main ways that we are trying to do that. One is called using essentially a magnetic container, which has the hydrogen in it and heats it up really, really hot and tries to control it. And if it's hot enough and it's dense enough, you would cause fusion to occur and release energy. So we can do that, but at this point it's hard or not possible to get out as much energy as we put in a sustained way. There is a big experiment that is being built in Europe called ITER, which will hopefully get to the point where we can do that with this magnetic bottling method. It's called the tokamak.
Yeah.
The other way that people are working on is the one that you were referencing, where you try to squeeze hydrogen down to a very tight volume, in which case this fusion can occur. And to do this, what they do in this lab that you are referencing is they have a little particle, a little container with the material, and they shoot it with lasers from all directions and heat it up and force it inward. And that can cause fusion and get energy out. And as you mentioned, there was a replication of the experiment that happened a while ago where they were able to get out more energy than the laser power that they put in. So as you say, they repeated it, which is a great important step. They were able to get even more energy out. We're still not at the point where we can do this in a total net gain of energy, which is the ultimate goal.
Yeah.
Once we get to the point, whether it's with this laser implosion type of method or this magnetic bottle type of method, the advantage of using fusion over fission is you don't have these huge amounts of radioactive waste, which is the main worry of the nuclear reactions using fission that we have now, because one, you have to do something with it, and it's radioactive for millennia, and two, you worry about people stealing it and terrorists and all that stuff. So we want to try to get away from fission eventually and get to fusion. We're not there yet.
All right, so the fusion would not have the radioactive waste. You wouldn't have any meltdowns, right? The power plants wouldn't have any meltdowns, like what's going on with Russia and Ukraine, and they're taking over that nuclear power plant. I guess geopolitical concerns also. Would that also be off the table if we got the fusion?
Right. I mean, you will not be able to the raw material for these fusion reactions are essentially hydrogen, right?
Yeah.
Which it's not going to cause a huge explosion and have a Chernobyl type of situation. So in that sense, once we get to the point where we can get energy, it would reduce our worries about people taking over and releasing radioactive materials into the environment and so on.
All right. So I did a little bit of research before, obviously, and it looks like the funding for fusion is just really not there. I know that with the new climate legislation, I think a lot of money was put into that, but the group that's doing the research or the work right now, National Ignition Facilities, is relatively small lab, and it's just a shame because in addition to basically being something that realistically could get us off fossil fuels, it would eliminate the need to mine and extract all these elements all over the world. Where are they? That causes all these issues, and how is it being mined and all that stuff. So that would also be, to me, it's just it's a no-brainer to focus on this. And I guess the long-standing joke is we're always 30 years away. And the article I read, actually, they said the joke was we're always 50 years away. So and I know I asked you this question the last time we talked about nuclear fusion. Do you think this latest advancement moves the needle, and maybe we're only 20 years off?
I think we are getting closer. So hopefully 20 years, well, hopefully sooner than that, but 20 years is probably not unrealistic. There's this experiment, and this is, like I said, one method, and this has gotten much closer. And then there's the magnetic bottling method, which this big facility is being built currently in France, and it should be coming online in the relatively near future. I can't remember when the date is, but that hopefully will also be either at the point where it's actually net producing energy, or very close to it, and get us to the point where we're actually able to use fusion in a actual energy producing fashion.
All right. So what is, what would the next step be in terms of scaling up to a degree that, could make this completely feasible globally?
Well, we need to get to the point where we can consistently run one of these reactors for a sustained period, which will take some time and research, certainly, right? Because, once we get to the point where we can produce the energy, we don't have the ability to build these huge facilities to put, in various locations around the world.
Yeah.
So we're going to have to get better at producing the energy, make it a smaller, more portable, although they wouldn't be portable, but a smaller type of setup, so that we could actually build these in a sustained way around the world.
All right. So now let's move on to the telescope, the James Webb. We passed the 1-year anniversary. I actually wanted to do this episode on the 1-year anniversary, but we're a little past it. And I mean, should I be saying so what? Or are we actually seeing things? Are we just, I know that there's a difference between observation and discovery, but let's talk about your favorite things that we've learned or seen. Maybe if you can even put it up on the screen.
All right. Let me see if I can share my screen. We seem to have a little bit of a lag, and you need to give me permission to do that. You go to security.
Talking about here?
No, security here. And then enable screen sharing right there.
Down. Okay. All right.
All right.
Learning things every moment with this
All
talk.
right.
There
All righty.
Wonderful.
So, there's the James Webb Space Telescope is performing phenomenally well. And they've done a whole bunch of very, very interesting science already. One of them, and there's no way you can cover everything, so I'm just going to do a few things here. So this image that we have here is the deep field view. So one of the things that telescopes do, the Hubble did this, the James Webb Telescope is done this, is point the telescope at one particular place and just hold it there for a long time. And what that enables the telescope to do is collect extremely faint light. So if there's very, very little light coming in and you keep staring at the same spot, eventually you build up enough of a signal that you can actually image it. So this allows you to see extremely far back in time. And one of the things that both Hubble did and James Webb Telescope did is one of these really deep field images. And that has enabled us to learn a lot about early universe. One of the things that James Webb seems to be showing is there are stars and galaxies at a time, the types of stars and galaxies that are very, very old are not what we necessarily expected. So something in the early universe is not exactly what we expected. And so that's interesting science, which is coming out from these deep field images.
Yeah.
So that's one thing that is very, very interesting.
I mean, look, going back to the first segment here and the muon and the standard theory, do those two, okay, we're trying to figure out all the particles in the universe, and now you're finding out that, hey, things maybe weren't exactly as we thought. Are those completely different spheres of knowledge, or are they sort of overlapping?
They are very much overlapping, especially in the early universe and in the very, very early universe. There's a lot of. Are we good?
Yeah, I think we're good. Let me just.
All right,
There we go.
Understanding the fundamental interactions and what's the makeup of all the things, the fundamental constituents of all the things that make up the universe definitely ties in to the
Origination.
the history of the universe, cosmology. That's what cosmology is. The other thing that ties into the standard model piece is, like you mentioned, the standard model doesn't have important pieces of what we know from other observations, like dark matter and dark energy. And dark matter and dark energy are, well, not dark energy so much, but dark matter is a crucial factor when we are discussing the development and creation of galaxies. So our understanding of how galaxies formed was the clumps of dark matter collapsed into smaller areas, and that brought in the normal matter, the baryons and stuff, which then formed stars and galaxies and so on. So these things are all tied together.
Okay. All right. So give us a couple of other revelations, discoveries, things that we've seen that excite you the most.
So I like this next thing, which is one of the most distant, what's called a active supermassive black holes. And the reason I like this is because black holes are just so cool. When you have black holes, they suck in everything around them. And if there's hydrogen, helium, other types of gases that surround the black hole, when the black hole sucking it in, it heats it up, and so it emits lots of light. And so that's what active supermassive black hole is doing. It's sucking in gas, and you can see the hot gas that's surrounding the hole. So that I think is really cool, just because black holes are super neat. This image is not really the image of the next image that I'm pulling up. It will come up in a second. There's a little bit of a lag, but this image is not a true image. This is a artist rendition. But one of the things that Hubble has been able to do recently is find or observe directly exoplanets. So as a reminder, exoplanets are planets that are orbiting other stars. It's not the first direct image of an exoplanet, but James Webb has done this now, which is just an interesting first step for this particular telescope. We've only really observed, I think, two. I think this is the second direct observation. I might be wrong about that, but it's one of the first direct observations of a exoplanet. This is an artist rendition, so this is not what it looks like. What it really looks like, and you can find this on the James Webb website, is you see a dot for the star and a little dot that's orbiting around it, which is the planet. And this is just, we know that there are lots of exoplanets out in the universe. Having a direct observation will allow us to do more interesting science. So that's very cool. One of the things we've been able to observe is complex organic material. So we don't know how life started, but organic material, meaning hydrocarbons and things like that, are definitely important in the development of life on Earth. There are organic materials outside that we've observed that are not like on Earth, but in space you can see organic materials. So that is one reason why we think life might be elsewhere. And this is one of the earliest time in the universe, so farthest back in time, image that we've been able to observe organic materials outside the solar system. So that is really super cool.
Yeah. I mean, so I know that everybody's like, oh, is there life in it? And now, I mean, I'm actually getting convinced that actually it might be the case that, I mean, not necessarily life like we have it here, but I mean, it sounds like there is enough evidence out there of life somewhere else.
Well,
Are we willing to say that? Yeah.
Well,
or we're not?
I don't think we can say that yet. I don't have what we've known for a while is that these organic molecules can occur naturally in the universe. It doesn't necessarily require life to produce them. However, one of the things that we believe to be true. Are we still recording?
Yeah.
Okay. One of the things that we believe to be true is that these organic materials were present in whatever that initial spark was that created life on Earth.
Yeah.
And so having those organic materials elsewhere
yeah.
makes us feel confident that somewhere in this vast universe, that spark may have happened elsewhere.
Okay. I think this is a good place to end. We're having a little bit of issues with the recording or whatever, but I want to go back to you as, you're now the dean of arts and science, University of Pittsburgh. What's exciting you the most about that position and the university, and, anything else you want to,
I'm very honored to take on this position as dean. It's the dean of the Dietrich School of Arts and Sciences. The school is a big school at Pitt, so it has the majority of undergraduate students. So the school has about 11,000 undergraduate students. I'm also the dean of the College of General Studies, which is a much smaller college, but its mission is to reach non-traditional students. And that is also a very laudable goal that I'm involved in now directly as dean. We also have, about 1,500 graduate students or so. Because it's arts and sciences, we encompass a huge number of different disciplines, from math and physics and chemistry, biology, to the social sciences, so political science, economics, anthropology, and so on, all the way to the humanities, communication, English, different languages, and to the fine arts. So we have theater, studio arts, music, history of art and architecture. So we cover a huge number of different disciplines, 30 departments, and a number of interdisciplinary programs. We have great faculty. We have unbelievable students, and it's really just exciting to try to help the faculty, the staff, the students, and their goals, and pushing knowledge forward and teaching the next generation of college students.
I'm very excited about it. I don't know that I know of any deans. So now that I know you, I can, I know being in the world of, academic world right now is maybe a little bit more challenging than in the past. But I'm going to leave it one last question about academics and your University of Pittsburgh. Where does artificial intelligence come into play now? And you're like, are you like grappling, like, what are we going to do with it? What is it? How do we use it? Do we not use it?
The fascinating subject, which definitely requires more than a couple minutes.
Yeah.
ChatGPT has thrust this forward in our conversation, in our discussions. It is a tool now which has enabled people to write papers and come up with ideas that was not possible just a year ago, right? And as a tool, it can be used for good or for ill, right?
Yeah.
The hammer can be used to, build a building or to knock someone on the head, right? And you want to use all of the tools that we have out there for good.
Yeah.
So things like ChatGPT and other large language model, artificial intelligence systems that are coming out is definitely a tool that we need to figure out how to incorporate into our research, into our education, and use it for good. So teaching students how to use it responsibly, understand the limits of AI. These things like ChatGPT can write a whole paper, but they'll also make up references, which sound extremely good, but they're totally made up. So you need to understand the limitations of these things. Human creativity at this point is still going to be relevant and important. So we want to make sure that we somehow, in a responsible way, take human ingenuity and creativity and then use the tool of AI in a productive way. So it is definitely a long story, and there's discussions about this on our campus and certainly on campuses across the country or across the world, I am sure. So this is something to still be figured out, I would say.
All right. So that's going to do it for this episode of Cut to the Chase. Adam, that was an amazing amount of updates and information. I do want to leave a tease because I want to bring you back in about, I'm going to say 6 months. And the tease is this: is artificial intelligence going to help advance, what we were just talking about with trying to figure out the particles, trying to figure out, what was going on a long time ago and all that.
You're still going.
All right. So here we are, folks. We're actually right next to each other. But, we're trying to, we're dealing with technology and all that. But anyway, so I will come back on that. And I'm hoping at some point I'll see some articles so I can get a little educated and sound like I know what I'm talking about.
That's good.
Adam, thank you very much.
Thank you, sir.
And that'll do it for this episode of Cut to the Chase.